Hello, everyone. Welcome to the second talk of the algebra session today. I am Tomoyuki Arakawa from RIMS, Kyoto University. It's my pleasure to introduce Syu Kato, who is a professor at Kyoto University, and he's going to tell us about the formal model of semi-infinite Flach manifolds. The floor is yours. Please.
Thank you very much for the introduction. I feel very honored to give a talk at ICM. And today I will report some construction of something called the formal model of semi-infinite Flach manifold. So as the title suggests, this is some particular model of something called the semi-infinite Flach manifold. That is a version of Flach manifold or affine algebras. So in order to say something, let us recall some story of usual Flach manifold. So starting from a simply connected simple algebraic group G over K, that is supposed to be an algebraically closed field, is supposed to be the largest and compact and G homogeneous manifold when K is taken to be equal to C. And this says that for if G equals SL2 or something like that, then X is supposed to be something like P1 or something like that. And the Flach manifold X of G realizes all finite dimensional G modules in a way it is feasible to study representation theory. For example, the Borel-Weill theorem realizes all finite dimensional irreducible G module by the global sections of line bundles, and the module character formula refines the structure of the Borel-Weill theorem, PRB-Kumar theorem, and that says that we have some particular components in the tensor product decomposition of two finite dimensional G modules can be seen as particular structures from the Flach manifold, and we can further refine the structure of finite dimensional representation of simple group G by using something called the standard monomial theory coined by Shashadori. Also, the Flach manifold X, or rather its quotient, gives a concrete realization of something called the classifying space of an algebraic group G that says that if we know the cohomology classes of this variety, then we can study some characteristic classes of G bundles and something like that. So, and it also has some it is also connected to the construction of some equivalent cohomology. And last but not least, the construction of Flach manifold basically categorifies the induction process seen in representation theory. For example, it gives the localization theorem that encodes the representation theory of real algebra G or group G, and also the Chevalier group representation theory of Chevalier group of G can be seen from dualistic theory when K is coming from the closure of finite fields. Of course, these four items are somehow mutually related, and it uses a word of its own. So after around 10 years from the introduction of Kac-Moody algebras, people began to study Kac-Moody groups, that is a version group coming from Kac-Moody algebra. Unfortunately, Kac-Moody groups are not algebraic group by itself, and it uses a slight diffusion from the theory of finite dimensional Flach manifold and so on. Particularly, if we start from the affine Kac-Moody algebra, that is a particularly important class of Kac-Moody algebras, then we obtain some affine Flach manifold, but it now comes by pair of thin affine Flach manifold and thick affine Flach manifold that has a slightly different, whose structures are dual to each other in some sense. And this construction essentially includes something usually called affine Grassmannian, and as we will see. And in any case, the realization of affine Flach manifold realizes some important part of representation theory of affine algebra or Kac-Moody algebras by the analog of Borel-Weill theorem and the module character formulas and so on. As I say, the future of affine D algebra or Katsumudi group algebra is a little bit different from the finite dimensional setting, and particularly in affine setting, affine and Lie group somehow uniformizes modular space of geometric data on curve, such as modular space of G bundles and so on. In this setting, we can describe the characters or simple highest weight module of affine D algebra by using the geometry of these affine Planck manifold in terms of casuistic algorithm. And this kind of thing is connected to something, a quantum group and some other algebraic structure by the heuristic program. So they are connected to more rich world of representation theory. Anyway, let me try to see what is affine Grassmannian for GL2. It is just written by a coset, and its numerator is something like this, and this is just a scalar extension of SL2 or GL2. And in the numerator, we have something like this, but here we see that we have all 4 entries, and these are not supposed to be 0. For all pieces. And this is different from the situation of the Planck manifold P1 or GL2. That is something like quotient of this shape by quotient of this shape with particularly 1, 0. So far, we see that the affine Planck manifold or affine Grassmannian is not just a scalar extension of something coming from the finite dimensional things. In the meantime, we have another object that is written like this, attracted attention. So here, we consider only G equals GA2 now, but the numerator is the same as that's coming from affine Grassmannian. But the denominator here contains 0. So this one is more likely more alike to the finite thing coming from P1. Anyway, we have some diffusion because we have some restriction on determinant and so on. And the first person who studied this kind of thing in heuristic, he considered the would-be orbit closure relation on here and connected to affine Grassmannian. He called this order generic Brillouin order by its construction. And later on, Ferdinand Frenkel considered some certain subset of this one and used it to realize some affine algebra and its representation at critical level. And later, following the idea of Drinfeld, Finkelberg and Milkovich constructed the variant of this particular set as a space of rational map, as we will say. And the construction of Finkelberg and Milkovich was later taken by some people, connect them to representation theory of some quantum group, and that is also connected back to affine D algebra by heuristic program. Approximately the same time as the work of Finkelberg and Milkovich, and Gibenthal and Lee considered a space of rational map from P1 to X and to define and study quantum K group of Planck manifold, or G equals SLN, and it is later generalized to arbitrary semi-simple group by Braverman Finkelberg. Unfortunately, our set X of half of infinity does not have enough number of functions such that we can look at it as an algebraic variety with Hausdorff topology. In order to recover this Hausdorffness, we should shrink the denominator so that we consider a little bit larger variant. That means that the numerator is again the same, but the denominator here, A and B, are more restricted. And then we get a map from this one to X semi-infinite, and this one has some Hausdorff topology. And this construction recorded in Finkelberg and Milkovich, but they are mainly considering something called a quasi-map space that will be the same as the Drinfeld compactification of the space of map from P1 to the finite dimensional Flood variety, and its Zastava spaces. Both of them are supposed to be a subset of this one with some structure of algebraic varieties. The future of these quasi map space is that they define some dense subset of this one. So far, we practically get all the information of this one by collecting the information of quasi map spaces. So we call this the Indo model of QG of RAT. But from the beginning, this QG of RAT was constructed as an algebro-geometric object. So one should be able to write this one down in terms of its coordinate ring. And this is what I am calling the formal model of QG of RAT. And the main reason we are considering about this is that if we can carry this program out, then one might hope to construct a loop analog of various subjects related to X, not only representation theory, but also some numerical problem which we will present. And the goal of this talk is to exhibit what is known and what we can do from such an idea. So in order to explain something more, we need to recall the classical construction of usual Flood manifold. So let me once again set G to be simply connected simple algebraic group over complex numbers unless specified otherwise. And then it contains a maximal solvable subgroup B that usually calls the Borel. If G is supposed to be SLN, then sitting inside here, B is supposed to be the upper triangular subgroup. We can take a maximal torus T inside Borel subgroup B. And our Flood variety is defined just as a coset of G by B. Because this upper triangular part can be split up by the diagonal part and the structure upper triangular parts, so we can divide this quotient by two steps. One is take G over N, and the other is to take the maximal torus that is supposed to be a diagonal things inside the something like this. And the advantage of doing this instead of this one is as follows. So as I said, that X is a compact variety, so its global function is just constant. But this one carries much more functions because of the algebraic Peter-Weyl theorem as described like this. Here, B of lambda denotes irreducible finite dimensional G module that is parameterized by its highest weight that is recorded by P of plus, and this forms a monoid. And this style is just a dual, taking dual. And if we do this one and consider as a graded by P plus, then we can put it a unique ring structure by considering some representation theoretic consideration. And if we consider this thing, we can recover X by just taking quotient, but somehow we need to subtract some irrelevant locus, but this is not so important here. And anyway, what I wanted to say here is that this is a general recipe to produce an algebraic variety from some tensor-compatible family of nice representations by using representation theoretic considerations. So far, this is a homogeneous coordinate ring of usual Flood manifold. And let us try to do something for affine Lie algebras now. So far, let G to be the Lie algebra of G, and associated to G, we have its affine Lie algebra G of Tudor. And in this situation, analogous to finite dimensional representation of G or group G for G Tudor are something called the integrable representation. This is defined as follows. So affine Lie algebra G Tudor is generated by some bunch of SL2s contained inside of G Tudor, somehow labeled by combinatorial data called simple roots. the module is called integrable if each of such SL2C action can be integrated into SL2C action. It means that we can realize this action as a derivation of this Lie group action. Because the Kato-Lie algebra and its Kato-Lie groups are not algebraic group, this is the best possible approximation of some algebraic group-like action for Kato-Lie algebras. And so this is an approximation of finite dimensional representation for Gay-Childa, and the classification of irreducible integrable Gay-Childa module with finite dimensional weight spaces goes as follows. And one is something called the integrable highest weight module that is quite popular and recorded in Katz's book. And the other is the integral lowest weight module that is the dual to the first item. Unfortunately, we have a little bit more. If we put the level to be 0, the category of representation is no more semi-simple, and we get much numerous modules. So we need to forget the idea to understand representation theory just by irreducible module and try to consider a little bit more general modules. And this kind of thing contains something called the global Y module that is supposed to be a maximal module that approximates the corresponding finite dimensional representation B of lambda. And unfortunately, if we start from integrable highest weight modules or integrable lowest weight module, what we get is a thin and thick affine varieties, so we cannot get something new. So far, we would like to concentrate into this case to say something a little bit different from the usual construction. So, to do this, let me introduce a little bit more Lie algebras. So let us set G of hat to be G of Childa divided by some D that records the degrees. For level 0 modules, if we consider the G hat action, we get it factors through further quotient that is just a scalar extension of G by a Laurent polynomial ring because the level is 0. For this one, we have some natural sub-algebra to not allow in the poles for G, and this is usually called the current algebra. Inside here, we have an analog, or affine analog of upper triangular algebra that is usually called the Iwafori algebra. That is taking a positive degree part here, and for the degree 0 part, we only get the upper triangular part with respect to the finest thing. And for the current algebra and the quotient of G hat, basically they are localized and integration to each other, so they basically share the same representation theory. And B tilde, that is supposed to be the upper triangular part, and generates the Kato-Lie algebra, but adding SL2 for each simple root. So far, we can induce this B tilde a little bit by using this SL2 action to induce up such that the SL2 action is integrable and maximal among all of the things. This uses something called the Demagil factor DI that is to mimic the integrability of modules. And the global Y module, W lambda, that is basically parameterized by dominant weight as the usual G, is known to satisfy the following recursive formula. So we choose some bunch of Demagil factor for collection of simple roots, applied. And we just put this one into this one to record. Then for some particular choice, we get the same representation as the previous things up to something Q dot. This Q dot basically records the grading that comes from G or the degree of G. So if we forget it, this is just an identity, but somehow they are different. And note that this kind of eigen condition is used in difference operators, and this DW is actually a version of McDonald's operators. So in order to say a little bit more about the homological property of this kind of thing, let me remind our adjoint property of De Morgan functors. It says that if we consider the suitable uniform modules M and N and consider the extension of them, then for we can transfer the effect of De Morgan functor from one factor to the other with some dualizing factors. And this is somehow written down explicit by our recent paper by Fagin and Magedonsky, but somehow something like that exists for a long time. And we have another construction due to Charlie and her collaborator that is usually called orthogonality that says that for each dominant weight, lambda and mu, we can consider the extension between the global Y module and another global Y module dualized. Then we have the condition that somehow it is non-zero if and only if B of lambda is isomorphic to the dual B of mu and zero and else. So this is different from this one, but this is to make this one one-dimensional. If we do not mind, basically we can just replace this one with this one. And this one, unfortunately, is valid only for characteristic 0, but this one works over G. So, also we can consider the McDonald eigen property with respect to dW that is also true for G. So if we plug this one to this one, compare the eigenvalue with respect to dW that is supposed to be put something like this by this one, then we see this part automatically for all characteristics. This is useful for us, the secure. And now we consider we can cook up some ring by our tensor compatible family. Because of the universal property of global Y module, we have a unique degree zero map from the global Y module weight lambda plus mu to W lambda tensor W mu. So dualizing, we get a commutative algebra with the same label set as the usual flat manifold. As we have the global, as we know the structure of global Y module reasonably well, we can analyze the structure with spectrum to see that we have a subset represented by following quotient. Here, for algebraic group E over C, E of Z is supposed to be the CZ valued point of E, and this is just a coset between them coming from G and N. And this is not a genuine. In order to upgrade this to capture the whole semi-infinite Frank manifold, that is to replace this one by this one, we need to consider a little bit more. To this one, we know that we have a global Y module X of lambda for G of Z, but here this one is something coming from just the quotient of this one. And we know that this one contains this one. And this one is basically a representation of affine algebra in a genuine way. So if we apply the De Morgan functor, we get the same thing by the integrability of this one. And inside here, we get the same thing, but to different degree and inclusion between them. And this kind of construction somehow approximates the global Y module of G hat by the global Y module of current algebra. And with this in mind, we can apply this De Morgan functor repeatedly to obtain a projective system of commutative rings, and the pullback of R by the De Morgan functor, and so on. Actually, these two are isomorphism if we neglect grading. But anyway, the natural construction uses a pure strict quotient. And we set Q to be just applying the construction for the usual Frank manifold to our ring R. That means that throw away some region that we do not like and just take the quotient. And this one is sitting inside of this union, and that is induced by this one. And we call this this union to be Q of that, and say that the formal model of semi-finite Planck manifold. The reason for this is that this one is supposed to be the universal scheme or in the scheme that represents assignments, such that for each ring R, we get some disco set. This one, unfortunately, this is not finely represented, but our Q of that is the initial object that approximates this function. And for the G equal SL2 case, we have and in this case only, we can write down it quite explicitly. This Q is just the projective space of infinite dimensional. This Q of that is a little bit amplifies a projective space. And somehow we need to do some union construction because we want here G inverse to be not equivalent. This is our formal model, definition of formal model. So we would like to understand its properties. And the first thing to ask for Planck variety is the Borel-Bell theorem as described as follows. For each weight and particular P plus, we have a line bundle O of lambda. And as the construction by Proj claims, if we consider the H0 or the global section, we basically recover as a global Y module by dualizing. And what is important here is that if we consider the higher cohomology, then it automatically gets 0. It is a very strong property of our situation. It says that basically, with respect to this kind of line bundles, this one behaves like an affine scheme, and it gives us to consider the numerical Grothendieck group by assigning T times GM equivalent quasi-coherent sieve Q to its Euler-Poincare characteristic twisted by line bundles whenever it makes sense. So this kind of consideration can give equivalent K group of Q or Q of that. So in order to say much more about the geometry of Q of that or the Planck varieties, we need to recall the usual construction of Schubert varieties and Richardson variety of the classical Planck varieties. Recall that we have a Chevalier involution of the pair G of T that sends B to be its opposite B minus, such that if we start with G, we can take transpose and inverse or something like that. And this sends the upper triangular matrices into lower triangular matrices and so on. And with this in hand, we can say a little bit. It is well known that the T fixed point of X is a bijection with a finite group W of G. And each B orbit in X contains a unique T fixed point and hence in bijection with W. So it means that if we have two elements B and W, we get a corresponding B orbit and B minus orbit, and we can take the intersection between them to obtain X of W of B. And if we start from the torus fixed point, B orbits and B minus orbit are basically some flows coming into that point and flowing that go out from that point. So the intersection is transversal, and the resulting intersection is either empty or irreducible smooth variety. The last thing is supposed to be Richardson's theorem. And we call the B orbit closure corresponding to W as Schubert varieties and X of W of B as open Richardson varieties. And this variety is supposed to know some intersection theory of X, as you can see immediately. So far, we would like to construct Schubert varieties and Richardson varieties of Q of that. In order to do that, we want to apply the Chevalier involution theta to this one. But unfortunately, this one supposed to swap G of G or G of this one to be the opposite thing. But unfortunately, this one is something coming from this one, not symmetric with a swapping G to G inverse. So far, we need to do a little bit more. And to limit this gain, let us try to remember the inclusion from G of B that is supposed to be X into something like this, or projectifying B of pi I, where pi I is supposed to be a fundamental weight. If we try to make it just tensor in C of Z and just quotient by C star, we get the inclusion by construction. And inside here, we can just extend the scalar from G to this one, because this one is not used as a ring or field, but just a vector space over C. And in order to say classify orbit, let us put B tilde to be the group that corresponds to the Iwafori algebra that is also formally defined as a pullback of the Borel subgroup by the evaluation at T equals 0, G equals 0. And then the Iwafori orbit of semi-infinite manifold is in bijection with affine Y group element of G because of the set theoretical interpretation. We just take the orbit corresponding to the affine Y group. We set the closure like this. And this Q of W is supposed to be our Schubert variety or semi-infinite manifold. And if we have this amplification, here theta that swaps G to G inverse makes sense. Inside here, we can apply something coming from the Chevrolet involution. And then we can take its intersection scheme theoretically to define our Richardson varieties. And here we have some W naught that is supposed to be the longest element of finite Y group sitting inside of affine Y group, but this is some artificial things and you can forget it. Anyway, we have defined such kind of Richardson varieties. With this, this definition is quite natural, and we can say that we can study its properties to say that this variety Q of W, B of W is irreducible and reduced and normal, and also we have an explicit dimension formula. This looks like a quite naive extension of classical result, but it has some serious implication. Let me start from this corollary. So this says that our as a consequence of our main result, we can identify the D-stable Richardson variety inside a semi-infinite manifold with a Dirichlet compactification of space of maps from P1 to X with prescribed degree, because we know that these two are identical as a set by some set theoretical consideration. So the scheme structure was very important for this identification, because if we want to actually compute something on that. So we would like to say a little bit more about the proof. The proof uses the Frobenius splitting of Q of rat, that is only considered for positive characteristic. But somehow the Frobenius splitting for the thin flap variety is known for a long time and very standard by using the both summation Demarge-Hansen resolution. But unfortunately, this one doesn't use this other thing automatically. So we established something like Frobenius splitting here and transplant like this and this and this. And the first step is done by my previous paper. And the next two steps needs a relation between integral lowest weight K modules and global Y modules. This requires the characterization, homological characterization of global Y module. So it's not so it's not trivial. Anyway, so this particularly use a relation between the formal model of semi-infinite manifold and the Indo model of semi-infinite manifold in a nice way. Let me try to say some application of this kind of constructions. to say something about the application, let me recall some small quantum K groups of Frag manifold. So small quantum K group of some variety is defined in terms of some compactification of space of maps by given Taro and D some years ago. This map is supposed to carry some marked point for t equal 2 or 3 that says that these xm are supposed to be a point to P1 and P1 map to X, and this compactification degenerates P1 to some chain of curves with arithmetic genus 0. And we have t equal 2 or 3 here, but if we examine reconstruction theorem, then we can reduce the computation to t equal 1 or 2. This is very important for us because if we have t equal 1 or 2, then we have map t to x. We can consider the pullback of B orbits, intersection pullback of B minus orbit. And if we can set the marked point to be 0 and infinity in P1, this kind of construction exactly yields some resolution of our Richardson variety of Q of RAT because of the identification of our Richardson variety and quasi map space defined in the previous section, previous slide. So therefore, if we study K-theory of Q of RAT, then we can understand the QK of X, provided if the singularity involved are supposed to be rational. So let me try to say a little bit more about, this is one thing needed to formulate application. Let me say another side of the things which are needed to formulate one application of our construction semi-finite Frag manifold, and that is supposed to be a Pontryagin product of affine Grassmannians. So we say that our affine Grassmannian is supposed to be something like this. But actually, if we consider its set of points, we can just identify this like this one. And also, if we consider the maximal compact subgroup K inside of G, we can shrink it further to something called the omega of K that consists of function S1 to K, such that F is polynomial and F1 is supposed to be E, and F is polynomial says that S1 is naturally sitting in C star, and this F defines a polynomial function on A and C star or C or whatever. And F1 is supposed to be E says that we just take quotient by K without this restriction. But anyway, so we prepare this form because they are homeomorphic to each other. And the reason we can consider this identification is that because this is a map to some particular group, so the right-hand side, this one, has a product induced by the multiplication on K. So it induces a product on the topological K group of this object omega of K. And this is this one. And if we compare the Markov factorization of maps by examining the poles of the maps, then we can identify the stratification of this description and this description, and consequently, we get an identification of G equivalent K group of affine Grassmannian together with something called the convolution product, and the topological K group of K equivalent topological K group of omega of K together with Pontryagin product. And unfortunately, we can also try to do something similar with other equivariancy, but it sometimes use a different result. But anyway, so we can also take some scalar extension from K to T, K to T or T intersection K to extend the scalar to obtain the T equivalent topological K group of omega K and transplant the structure to here. This is our understanding of the Pontryagin products on affine Grassmannian. With these in hand, Lam and Lee and Mihachi and Shimozono conjecture that if we somehow localize the T T equivalent K group of affine Grassmannian, and also localize the T equivalent quantum K group of X, then we get some map that is supposed to be some isomorphism. Here, this localization is quite subtle. That means that we have natural multiplicative system on both of them, which I didn't say much about that. But anyway, so these are supposed to be opposite direction to each other. It means that, so if this is isomorphism, we can take the quotient of this one. This is just a K of X. So this is supposed to be a very small part. So somehow this isomorphism seems to be quite non-trivial from our perspective. And as I say that, somehow this one knows the quantum K group of X, so we can construct a map like this. And here, these two are supposed to be quite intimately related. For example, from the study of automorphic forms and so on, so far it is natural to expect an isomorphism between these two. And we can just try to construct a map by brute force and try to see what happens. Then what we get is that we have this kind of commutative diagram which respects the Schubert basis and natural operations on this object. Our construction here is so natural that we get the parabolic and non-commutative versions and so on. We also have the homology version of this bottom arrow, and that is usually due to Peterson and Lam and Mihalcz and Shimozono. And we can prove this by using our QSI map space, but unfortunately, we do not know, we do not completely know what does it mean. So at the moment, this is not a triangle in the homological version. And I think this says that this kind of consideration of semi-infinite Frege manifold has an actual application or interpretation in the previously existent numerical problems. This is what I can say from me. And let me say something we would like to do in the next. So as I said, that our semi-infinite Frege manifold leads a version of Frege manifold, and Frege manifold are supposed to study for long years, and we have numerous results on that. And we expect virtually all results in geometry of X and the descriptions would have some reasonable analog in the setting of Q of RAT. This is what I think, and but anyway, so yeah, so this is what I think. And also, actually, the above triangle gives a little bit finer structure of QKOT using the semi-infinite Frege manifold. This finer structure basically somehow contains shift operators and so on. And also, our Q of G of RAT is supposed to be an algebraic version of some loop space of X, the usual Frege manifold. So our homomorphism psi, that is an instance of some loop space formalism, description of quantum cohomology of X, should exist in much greater generality, but we cannot say much about this at the moment. And the fourth thing I would like to say is that we have global counterparts in each piece of the above objects in above triangle. So we would like to connect the global versions of the triangles, but so far I do not think I understand something. And the fifth thing is a little bit boring. We would like to consider the tensor product decomposition because the classical geometry of Frege manifold use the PRV theorem as some nice consequences, but I think we need to replace some things with some conformal instead of the usual tensor product and so on. But anyway, we should have some nice theory with this replaced objects and so on. And finally, let me advertise a little bit that now we slowly understand the vector bundle on QG of RAT, and this would have some give us some information about some representation theory of affine algebras and so on. And anyway, we would like to continue this investigation and would like to equip the geometry cube rat to some full citizenship in the world of geometry and representation theory. Thank you very much for attention. This is all what I wanted to say.
Thank you very much for the very nice talk. There's no time for questions, but you can ask questions on the Discord platform. So let's thank Syu again for the very nice talk, and bye-bye.